Parallel circuits, so resistors connected in parallel. So with series, your first and your last resistor are connected to your voltage source. Current is constant. Total resistance is equal to the resistance adds. Put that in a simpler way. Total resistance is always larger than the largest resistor. Okay. And you have what's called the voltage divider, which means that each resistor drops voltage proportional to its size and relative to the total resistance of the circuit. Okay? So this resistor with the largest ohm value drops the most voltage and produces the most power. In circuits with two or more resistors, the resistor with the smallest drops the least. The sum of the individual voltage drops equals applied voltage. As resistors are added, resistance goes up, total current and power go down, and it flips around whenever it goes the other way. You start taking resistors away, total power goes up, total current goes up. Okay, so we're going to be talking about resistors in parallel, voltage in parallel, Kirchhoff's current law, conductance, total parallel resistance, Ohm's law in parallel circuits, power in parallel circuits, troubleshooting, and this is known as a current divider. So resistors in parallel, when two or more loads are connected between the same 2 points, they are in parallel. Each parallel path is called a branch. Okay? Current is divided in parallel among those branches. If there's more than one current path between 2 points, you have parallel circuits. Give y'all just a minute to write that down. Okay? Everybody good? All right. So here's some examples. You have your voltage source in the center right here on this first one. But if you look, every single resistor connects back to this same path. That is parallel. It's the same as if you write it in this format, where you have the voltage source to one side. But the fact of the matter is, each resistor creates its own path. All right? That is the whole purpose behind this. Each resistor creates its own path. Everybody good? So, looking again, each resistor creates its own path. You have your resistor here, has its own current. The next resistor has its own current. Doesn't matter how you configure these, as long as each resistor creates its own path, and is isolated into parallel from the other, you do not have a series circuit, you have a parallel circuit. Okay? Okay. So this should look familiar. We had something similar in series. Let's look and see if each resistor creates its own path or if we are in series circuit instead of parallel. So from the positive side, we can trace this to each resistor and to only one side of each resistor. And if we look at the negative, we see the same thing. It touches one side of each resistor, making a complete circuit without the paths crossing once. So each resistor will create its own path across the source voltage. Does that make sense? This right here is the majority of how our homes, our cars, everything is wired. Yeah? This is the majority of it.
Basically, each branch touches a resistor, negative and positive side.
Yes. That's exactly what you're looking for, is for each branch to touch both the positive and negative side of a circuit. Okay? So these were being put into parallel. It doesn't matter how I do it. I can go straight across both sides. I can do all sorts of shapes with this, but the main thing is that my side A will never touch my side B. I can lay the wires over each other, but they will not cross and actually touch. So voltage in parallel. You probably have seen this and never really understood it. Each branch is connected across your supply voltage. So total voltage is across each branch. Why does a plug always have 120 volts? Because it's in parallel. Why are every light that you come across 120 volts? Because they're all parallel, right? They all connect back to source. They're all across that same positive and negative run. Okay? So you literally have full voltage across every light. You have full voltage in every plug. The main things that power our house, and there are exceptions in your higher power three-phase motor, things like your refrigerator can be three-phase. Generally, I think it's still 120. You have your washer and dryer. You have your oven, stove things. So everything in your vehicle is wired for 12 volts. Your headlights, your radio, your taillights. And what all produces that 12 volts? Your battery produces that 12 volts. Hello. Yeah, give me just a second. Let me pause this. So, back to what I was saying. So, your battery in your car produces 12 volts. Everything in your car requires 12 volts. So, everything in your car has to be wired in what? Has to be wired in parallel, right? Okay. This is a good idea of a car wiring diagram. Anybody who's taken PLCs? What is another name for this? No, this is actually what's called a ladder diagram or a ladder logic diagram. The whole purpose of which is to show you how everything is put together. You have your positive side and your negative side, and you can see how everything is wired in between. Okay? You have your switches, you have your fuses, you have your voltage regulator that's controlling everything. Your alternator. What does your alternator do, by the way? It recharges your battery. That is the whole purpose of an alternator, is to charge that battery. Yeah, we're not going to talk about what happened the other night to my battery. I'm close to needing to change the battery, but then the battery faked me out the other night. So we're not going to talk about that right now. We'll talk about that another time. So as you can see, everything is across your voltage. Okay? Everything goes across your voltage. What about well, the reason we use dwelling is because not everybody's in an apartment, a house. You have motorhomes, you have all sorts of different places that everybody lives these days. So what is the voltage available on all of your low voltage power receptacles? It should be what? Huh? In your home. 120 should be the average voltage that you put. If you were to take a meter and put it to a light socket, you should find 120 volts. Ish. Sometimes it's around 110, sometimes it's somewhere in that. Your lights should all operate on 120-ish. It's not ever exact, but it's close. High voltage devices operate on what? Maxed out, it's generally 240. It can be less than that, but it's maxed out at 240. So your entire electrical system and your place of where you sleep. How about that? In the place of where you sleep, everything should be wired in parallel. Okay? Everything should wire in parallel. All right. So your National Electrical Manufacturers Association has two different types of plugs. And they're different for a reason. NEMA 5s are meant to only go up to 15 amps and thus only allow you to plug in for 15 amps. Okay? What does that mean to you? Or what should it mean to you? Is that this particular plug only puts up with you putting 15 amp circuits on it. If you get something that's 20 amps or higher, you need to move to the other type of plug. The other type of plug actually looks like it does because 20 amp devices are supposed to look kind of like that in the plug section of it. Where normally we have two parallel plugs and you have the center that grounds it. This one actually takes one of those plugs and turns it sideways. And you still can have that, and you still have that ground. One of the few ways that NEMA's trying to look out for you. But that's supposed to be rated for 20 amps. Okay? Alright, so this is how your basic residential wiring is. You have your positive and, you have your hot and your neutral. And these days you also have a ground line to just about everything. Why? Because grounding something out is safer than having it ungrounded. Ground means that it can take excessive current and just feed it to ground and it's not going to damage anything. Okay? This is how we protect ourselves. And we don't use fuses anymore, do we? What do we use? Breakers. Why? Because breakers keep us safer. Well, I shouldn't say that. Breakers are harder to put something in that you shouldn't.
Not with a breaker, but with a disconnect. I had to test the unit. It was very funny. So, 5 minutes when this happened. No. It was 5 minutes or half inch. I don't know, but I had to put it in. Believe it or not, next thing you know, I already knew there was an arc flash a little bit. It was out of church. I was like, you know what? They need to get an electrician because I didn't have those certain type of resistors. No, the fuses. I didn't have those fuses, and I had to turn the unit on to see what's happening to the unit. Turns out it was an electrical issue, so I told them to get an electrician. It was part of it.
You're not ever trying to become the electrician, huh?
I had to do what I'm legal.
No, I shouldn't say it that way. If you are not an electrician, don't play at being one. That should be a worldwide rule.
I did what I did with the disconnect to get power in my unit, see what's acting up. Turns out
Yep.
electrically.
And that's fine. Just make sure that if something like that is happening, that they know to call that electrician. Don't try and.
Yeah, I'm a journeyman.
Because there's a lot of people that will sit there and go, "Oh, you just have to fix this," and they're not the electrician. You need to make sure authorized. When it comes to electricity, authorized personnel only should always be your mantra, guys. If you're the authorized person, that's great. If you're not the authorized person, make sure that they know they need to get the authorized person. Oh, always. Have insurance and be bonded. Yeah. Find the voltage across each resistor. So what should my voltage be across each of these resistors? It should be 25 volts. Why? Because they're all in parallel, right? They are all in parallel. Yep. We're about to find out. So what are each of the resistors' currents? So each resistor has 25 volts. That's not a resistor. That's. By the way, what is that sign for? It's a fuse. That is the very simplest form of drawing a fuse. No, a fuse does not really look like that in real life. What you're looking at is a schematic. Just like resistors don't look like these, fuses don't look like a little half moon, two half moons facing against each other. But it does represent what a fuse does, because what a fuse is a little piece of wire that's just about nothing, that breaks at the drop of a hat if you get too much current moving. So we have 25 volts at each resistor. Okay? 25 volts to each resistor. Okay? So what is my current at R5? We have 25 volts divided by 3,300 kiloohms. 3,300 ohms, rather. 3.3 kiloohms. Oh, correctly. Huh? 7.57. 57 milliamps. What about at 2.2 kiloohms? Yes.
And this is how we get the parallel, right?
All right. So what about 25 at 1K? Should be. And at 1.8. All right, so what we have is 13.9 milli, 25.0 milli, 11.4, 11.4, and 7.57, correct? All of these would be milliamps, yes? Okay. So if I was to add these up, what would I get? So we're adding these up. 69.27. Again, that's milliamps. So what is my resistance total? We have our voltage total, we have our current total. 25 divided by 69.27 gives me what for my resistance total? 3 what? 360.9.
Okay. No, it's million.
25 divided by 0.06927 is 360.
Yeah.
Well, I'm going to put it as, 360.9 ohms. It is ohms.
Okay, so, this was when it's in parallel, right? When it's in parallel, you got the voltage total, and to get the resistance total, you got to do the voltage. You do the voltage divided by the voltage divided by the resistance.
Divided by current.
Current, okay. You do voltage divided by current. So you get all the current and you add that, and it's gonna give you resistance. Voltage divided by current. Right. Okay.
Yes. Because guess what? I put it up here and I left it up here for a reason. Ohm's law still applies, as long as we're dealing with electricity of any sort. This rule right here is permanently applied. It's a different format, yeah. Well, the whole point of it is to be in a different format at this point because we're looking at a different type of circuit. So the thing about a parallel circuit versus a series circuit, series breaks the voltage across all the resistors. Okay? Just like a train moving through its route. Each car holds its own weight, and so the train has to pull that weight. And it's having to pull more for each car depending upon its weight, right? That's what we mean by voltage divider. The heavier the car, the harder the engine has to work to pull that one car, as well as all the other cars with it. Well, yep, I gotta think about that. What we have here is a little bit different. Instead of one train that's pulling one run of cars, let's say it has 10 cars behind it. Instead, what we have is more like you have several tracks and each train only gets one car with it and it just goes. Same train on each track, everybody has a different car behind it, but the speed's going to vary only by how much weight that car has in it. Does that make sense? Or you can even consider it like the highway. You've ever been on the interstate with 3 lanes open, everybody has one car. Every car has the same engine. How fast you go is going to depend about how much weight that car is having to pull. Right? That is parallel. Very big difference between the two, right? Very, very big difference. And yet it is still the same because what? Ohm's law still applies.
Basically, it's the same thing. It's just parallel series circuits wired in the same manner.
Finding the amperage.
Not so much. There's the same in the fact that you can actually reduce these down to a simple circuit. Instead of a series circuit, you have a simple circuit in each circuit. Does that make sense? So if you remember back in intro, when you only had that one resistor circuit, that is known as a simple circuit. These are nothing but simple circuits just added to the same voltage source. Does that make sense? Okay. So series and parallel formulas. Let me put it this way. Ohm's law and Watt's law are not changing. They still apply. Okay, now we'll write that up here too. There you go. Ohm's law and Watt's law still apply. Okay? Power will always add. Unfortunately, the power company doesn't let us get away with it the other way around. Power will always add. The more lights you turn on, the more power you use. I'm sorry. It's unfortunate. It happens. So Watt's law is still in effect. These are not going away. And there's a reason I'm emphasizing this, guys. And you'll see whenever we get there, because I will probably rant and rave about it, because it's a very common thing that people have a misconception of. Okay? So before we get to that point, we have what's called Kirchhoff's current law, and that is that the sum of the currents into a junction. So a junction is where each of these resistors connect to the main line. So the sum of the currents into a junction equal the sum of the currents out of that junction. Okay? Current in to any place of this must equal current out. What that means is that the current I put into this circuit is the current I should expect to find in the circuit. Okay? So whereas we had, we'll go back to an even older analogy. A series circuit. One nice long winding river, you've got dams across it every so often that are using the water to create power. Right? That is a series circuit. A parallel circuit is what you're going to find at the very end of that river, where every part of it has its own path. And in this case, we put a dam across each of these paths to say we're going to make hydroelectric power in all these little places. Okay? You still have the full push of the river before it, but the speed is going to be determined by the size of these dams and how much water they're forcing back. Does that make sense? Series, parallel. Okay? So current will always add in parallel. What we just did a minute ago with that previous circuit, current adds in parallel. Okay? Everybody understand? Are there any questions before we move forward? All right, so looking at this, we're looking at the path of current flow. So current in equals current out. So whenever I put a battery to this circuit, my current will follow the negative line, of course. Why is it following negative? What are we moving when we are moving current? Electrons. We're moving electrons. We cannot move protons because why? Because the nucleus of an atom if this was the nucleus of an atom right here, you are not busting that up. And no, that is not a great drawing, but that is the best you're going to get out of me tonight. Protons are very tightly bonded to their neutrons. They don't want to be separated. The only way you're going to separate those is with very, very powerful machinery that is very, very expensive. Nuclear? It's what?
Wait, so not all
What?
The bomb. Wait, are all bonds
Actually,
like
yeah.
this?
Huh?
So all bonds cause the proton to split, or is it just the hydrogen?
No, what you're looking at that for is you're looking at true nuclear material. True nuclear material, things like carbon-14 that have a half-life every such and such often. I don't understand half the time when nuclear is being explained to me by people that want to get very technical with it. Oh yeah, you start splitting atoms, you are basically releasing a heck ton of energy that cannot really be contained. It's the reason why let me put it to you this way. Most explosives are based upon just moving stuff out of their way. Okay? If you talk nuclear explosion, it's why something as the size of the bombs that were dropped in Hiroshima and Nagasaki caused far more damage than, let's say, just put it this way. It was megatons of an explosion versus a TNT explosion is very, very tiny for but for all the damage it does. But one of the ways that they do mining is they set off explosive charges. They can do that safely and not have problems with it, with nuclear material and all that, because that's not how those work. If they were to set off an H-bomb, you are talking a lot more damage, as in it would probably take out the whole mine. And then some. Blow it right out of the ground. Basically, have you ever seen somebody dig up an anthill after they pour aluminum into it? That would be what happens if you put an H-bomb in the ground. It will go off, and it will take everything like that out of it, and you might even have some problems with that. So when you're splitting protons, that's more of what you're going to get. You get a lot more energy, but you create a lot of damage too. So it's not good. It's not something you want to do. So that's why I'm trying to emphasize the fact that we mainly we don't split atoms to make electricity unless you have a controlled nuclear reaction. And I mean controlled. You do not ever want to be outside of that control. That's what happened at Chernobyl. Yep. That happened in the late 80s, didn't it? Like 88, 89? Somewhere in there? Yeah. That's the kind of explosion you really don't want. So we do not want nuclear explosion, so we move electrons, not protons. All right, so total current here is 24 milliamps. Current at R1 would be 12. Current at R2 would be 12. Total current again is 24. Current in should equal current out. Okay? Any questions on that, guys? All right, so total parallel resistance, current, and power. Basically, totals are the only thing that will change depending upon what you change in the circuit. Now, I'll explain that in a little bit, but we're going to go ahead and finish this. As resistors are connected in parallel, total resistance of the current decreases. So thus, total current and power will increase. And those of you taking notes, I'm going to go ahead and underline a couple things. There's a reason I am underlining the word total. You'll see it in a minute. when we talk about some other things. All right. As parallel resistors are removed, total resistance increases, total current and power will decrease. The total resistance of a parallel circuit is always less than the ohm value of the smallest resistor. We'll get into why that happens in a minute. Okay? There is a reason I have underlined the word total. Why do y'all think that is? Just kind of a guess now before we get to it. Parallel.
Total of the whole circuit is like the number you would go off of. Technically, you know what I'm saying? That's how I think about it.
Close, but not quite the answer I'm looking for. Anybody else want to take a guess? Let me put it to you this way. Tell me something. The brightness of the bulbs change just because I do this? What about if I do that? Does your bulbs change in brightness?
That was better, the way it was. It was just, it was better.
Yeah, we need to dim the lights a little bit. My eyes hurt. Oh my God, Miss Book. Thank you so much. I have a lot of contestants.
Okay, we'll leave the lights off up here. Okay, but you get my point. None of the lights change their brightness just because I cut off the others. Okay? I want you to think about that and kind of digest that for a second. What that means, and what I'm trying to tell you with this whole underlining of the word total, is that the totals will change of the circuit. However, are the individual values of each resistor going to change? No, it's not. The individual values. So let me put it to you this way. If I completely cut off one river, one or two rivers right here, is that going to change the amount that's able to come down these? No, because it can only still come down so much, right? That is the point. The total might change, but the individuals can't. Okay? You have a parallel circuit. The individuals will not change. Your voltage cannot change because it's parallel. What stays constant through a parallel circuit? Voltage. If your voltage doesn't change, can your resistor change value? No, your resistor cannot change value because your resistor is a fixed resistor. The only time a resistor will change value is one of three options. Either your resistor has become open, your resistor has become short, or you've got a potentiometer slash and or rheostat, which is a variable voltage, variable resistance device. Okay? If one of those three conditions are not met, your resistor will never change values. Okay? If you're looking at it as the dam analogy, once a dam is built, you can't build it higher, you can't build it shorter. It is what it is. Okay? That is what you have to remember with these. And it is the one thing everybody has the biggest problem with. I don't know why. Your resistance isn't changing. Your voltage isn't changing. Is Ohm's law changing? No, it's a law. It is the firm thing that will not change. So if resistance isn't changing, voltage isn't changing, current cannot change. The holy trifecta has been permanently bonded. You are not going to change them. Your individual powers will not change. However, the overall total of the circuit, will that change? Yes, it will. Like I said, that is probably one of the biggest things that people tend to forget. That is why I've underlined it on here. And that is why I'm trying to get y'all a way to remember that, because it is one of the more fundamental concepts of parallel. Okay? So let's talk about reciprocal. And there's a reason for it. How many of y'all remember reciprocal from intro? Us talking about reciprocal, that would have been in fractions. What is a reciprocal? Doing what with a bottom number? Taking it and flipping it. So a reciprocal of 4 over 1 is equal to 1 over 4. Right? And we're not going to go into all the rest of this. It's all getting too complicated. We're going to leave it at that. If 1 over 4 is equal to 4 over 1, that is the reciprocal. Now then, when we were in intro, we talked about what's called conductance. That ring a bell? I told you it would come back, right? Told you we'd be using it in DC. There is a reason for that. If resistance is an indication of the resistor's ability to block current, the reciprocal of that is the ability of it to pass current. That is conductance. The reciprocal of, okay, so that is where you got the G is equal to 1 over R. The inverse of resistance is conductance. In a parallel circuit, to calculate total resistance, you have to find total conductance first. And then inverse that to get your total resistance. Yes, this is about to get to be a lot of fun with math and numbers. Don't panic on me yet. All right. Everybody good? Anybody need a second? All right. We're going to get through conductance, and then I'm going to give y'all about a 10-minute break. That way everybody can kind of get up and stretch and nobody starts trying to fall asleep on me. Well, we're about halfway through anyway, so. So when calculating total conductance, we're dealing with the inverse, right? So what that means is you're adding those inverses. And I can actually hear y'all asking, why would we add the inverses? Because total resistance is less than your smallest resistor. Okay? Adding the number 4 3 times is a far cry different from adding 1/4 3 times. Right? In one way you get 12, and the other way you get 75 cents. Right? All right. Resistance from conductance is where you take the reciprocal of resistance to get conductance. So thus you take the reciprocal of total conductance to get your total resistance. You take the reciprocal of the reciprocal. Yes, you do. You flip it, add it, flip it back. So think of it like, how many of y'all like to eat pancakes? Well, let's put it this way. So what you're doing is you lay the batter down first, you flip it one time, put more batter on it, and then you flip it back again. How do you make a bigger pancake? Or how many of you have seen the waffle makers? I don't know if if they've ever had them outside of like a giant buffet or a hotel or anything, where you pour the batter on, you flip it over and open it to pour the waffle batter in, close it, flip it to cook it, and then you have to flip it back and open it to get your waffle out. Y'all ever seen those? They're really cool. Make a really good waffle too. I'm hungry. So solving for RT. Yes, this is actually what this looks like, and yes, it's fun. It's fine. You take the inverse of the added inverses to find RT. So what you would do first is inverse all your resistors, add up those inverses to get your total resistance, and inverse your answer after that. Flip them all, add them, take whatever you get as your total and flip it back. Flip, add, flip, yes. Exactly. That's a good way of saying it. Flip, add, flip. Pretty much. Flip, add, flip. Okay? All right, so this one where they did a series circuit, I don't know why they put that in the middle of this. I've got to move that, and I've got to remember to do so. So reciprocal of the sum of the reciprocal is basically what this is called. I like yours better, flip, add, flip. That works much better, and it's a far easier thing to say than reciprocal of the sum of the reciprocal. Personally, I want somebody to say that 10 times fast without tripping over their own tongue. Just saying it fast, it becomes a tongue twister after about a minute or two. One of the ways, I won't even say y'all should remember this, because most of the time if you're dealing with parallel circuits, you're not dealing with just two. Okay? But if you do happen to have resistors of the same value, say you're putting in a bunch of lights, this one actually does work. You take your resistor and you divide it by the number of resistors. So let's say this has 10 lights. If each of those was 100 ohms, divided by 10, you'd have 10 ohms per light. Or a total of 10 ohms total. Yep. Pretty much. So total parallel resistance, the number of current paths affects total resistance. Connecting the resistors in parallel increases total current and decreases total resistance. This is why it's so dangerous to say that a different way. At Christmas, how many of y'all like to put as many lights as you can in your house? Or how many of you like to over-decorate a room or have way too many things plugged in? Any of you? Or does everybody know better by now because they know that increasing that total current is going to increase the likelihood of what? The more loads you add, in other words, the more things you plug into that circuit, the more likelihood you are of tripping your breaker, hopefully, tripping a fuse if you still have those in your house. If it does not trip the breaker, and certainly if it did not trip the fuse, that wire behind the wall gets really hot. It's also next to wood and insulation that like to burn. Little house fire. Ooh, but at that point, it's too late. So connecting resistors in parallel increases that total current and therefore decreases total resistance. The less resistance you have, the more current you have. The more current you have, the more heat you have. The more current and heat that you have. Everybody see how it starts running away? This is why homeowners should not put in larger fuses or larger circuit breakers, because the wire can only handle so much. The wire is only rated for either 15 or 20 amps for most circuits in your house. That circuit breaker is rated for 15 or 20 amps according to the wire. If you overload that circuit and have it switched out for the wrong circuit breaker or the wrong fuse and circuit breaker are supposed to give up first. If they can't, the wire will go next. All right, guys, I'm going to pause it right there, and let's go ahead and take about a. All right, so Ohm's law in parallel circuits, current adds, voltage is voltage, resistance total is flip, add, flip. I really like that one. Okay. So different ways to solve for RT. I said if you just can remember the flip, add, flip, there you go. But if anything else, you can also still use voltage divided by current to get resistance, or power divided by current squared. Either way works. So solving for R of X. So R of X means that if you have a resistor in the circuit that you do not know, you can do voltage divided by current if you know those. You can do power divided by current squared if you know that. Or you can subtract your flip, add, flips. Instead, you can subtract. So flip, subtract, flip. There you go.
What makes it kind of complicated, earlier, because after we get the resistance total, it's not it.
You have to flip it back.
Right.
Yep.
As in the series circuit, we just
Hopefully.
just.
Yep. Now, this formula right here would work the best. The Rx is equal to the inverse of all your resistances subtracted from your resistance total as their inverse selves. How about that? you don't have resistance, but you have conductance. All you gotta do is flip the conductance to find the resistance. In this case, you're flipping the resistance to find the conductance and adding or subtracting the conductance to get. Okay, in this case, what you're doing is you're finding the conductance for each resistor. Then you're subtracting it from your total resistance's conductance. So you're taking your total conductance, subtracting everybody else's conductance, and then taking what you have left over and finding your total, finding that specific resistor, if I can talk. Huh? So what you have here is you've got the resistance total. Yes? So just like with series, you can subtract your resistances from your total resistance to find the resistance you're missing, right? Only instead of using the resistances themselves, you're using their conductance. Yes, you're just using their conductance instead of the resistance value. You just have to make one extra step on each resistor.
When you actually do subtract that, you still have to divide it by one.
When you divide it by 1, you are flipping it. You're dividing 1 by that number is how you flip it. So it goes back to that, the inverse of 4 is 1/4. The inverse of 1/4 is 4.
Yeah, I was just saying, I don't know if the formula is using it, basically, you don't, when you're doing the 1 over whatever number it is divide.
You've got to. Let's put it this way. There's an easier way to write this. I'm going to go ahead and write it under here. Rx equals RT -1 minus R1 I don't know if y'all can see that up here. Because this button right here on your calculator exists on just about every calculator you have in the world. And it is what is called the inverse key. So everybody look at your calculator, you either have an inverse key that looks like x to the -1, or it's going to be 1 over x. Okay? Down yours?
So do you have to press second? Second puts you square root.
Yes. Right. Get calculator out. There is a key for this, guys, on every calculator. That's ours on this one.
What are you saying?
sounded on yours?
Yeah, I know.
That key right there is probably the fastest, easiest way you're going to do all these. You do not have to do 1 divided by your number. You just have to hit that one little key and there you go. Does that make sense?
I mean, here's the letters. -1. That applies kind of twice because you have the -1 to each of them.
Yes. Does that make more sense? Writing it out that way? So R of X is equal to the inverse of RT minus the inverse of each resistance. You take all that and you find the inverse of that answer, and there you go. Yes, that's exactly what you're looking for. Let me put it to you this way, put it in a different way, guys. The reason you would use Rx is equal to all that is if you can't find B and you can't find I, and you cannot find P. If you cannot find B, I, or P, at least 2 of those 3, you have to use that. Yes. But in this case, you're flip, subtract, flip. Okay? Like I said, generally if you're finding R, it's kind of like finding I or V or P. If you have the other 2 variables, you don't really use the long formulas. However, if you have to use the long formulas, it's nice to know what they are just so you have them on hand. Use them rarely. I will not say you don't use them, you use them rarely. Okay? You don't use them as often as you would use Ohm's law to do this. Ohm's law is the faster way to do it. Well, I'll put it to you this way. The reason you want to know some of this is because if you're, let's say, an electrician, you kind of need to know what loads you're going to be wiring in. Because if you wire in the wrong loads, you lower the current, lower the resistance too much, and you're going to excel the current so much that you end up burning something out. Master electricians have to know what they're doing. And this is part of what they have to know. Because if they don't, they ain't just risking their lives, they're risking the lives of a lot of people. So solving for IT, you can add it, voltage divided by resistance, power divided by voltage, square root of power divided by resistance. So same formulas we've always had with these. They all go back to Ohm's law, Watt's law, right? Solving for branch current, again, all goes back to Ohm's law, Watt's law. Once you have a branch in a circuit, is anything about it going to change? Not unless you're changing the voltage of the whole circuit, right? Or if there's no what? If there's an open, not unless it's a main line open. Or if you have a short. A short is where it's going to mainly change. Opens, not so much. That is the good thing about a parallel circuit is that your opens don't change anything. If you have an open, let's say here's this very simple circuit. If I have an open here on my 5K, it's technically not going to change anything for the 1K. because the voltage still hasn't changed, your resistance still hasn't changed, your current can't change, so nothing changed. What changed is the overall resistance, the overall current of the circuit. Does that make sense? The individuals don't change. It's the overall that will change. Does that make sense to everybody? Okay. So same thing here. If I have an open on any one of these circuits, again, it will change the overall. If I have a break in the circuit right here, it's going to double my resistance in the total circuit. And I'll show you why. If everybody's got all this over here, we're going to erase it, and we're going to talk about the differences between opens and shorts a little bit ahead of all this, just because it kind of fits in what I'm trying to explain. All right, so we know everything's going to be 12 volts. I don't know why I'm writing with marker when I can write with the whiteboard pen. Everything's 12 volts, right? Because it's all in parallel. So that means that everything's probably going to be 12 milliamps. If I had to guess, my total current is 48 milliamps. My total resistance is 250 ohms. Somebody tell me I'm right. I'm right? I just did all that in my head. Yes! No, my total resistance is 250 ohms. Yeah. What's a quarter of 1,000? But that's just because I've done this fast enough and I've done this often enough that I can have that almost pretty much memorized. What can I say? It's parallel. Mm-hmm. The inverse of 1 kilo ohm is, if I remember right, 0.1. Or is it 0.01? Yeah, it's 1 milli. So it'd be 0.001 for each one of these. When you add up 0.001, your overall conductance total is 0.004. If you take 0.004 and take to the -1, what you get? 350. That x to the -1 key. Or the 1 over x key, whatever y'all have got. Okay? Like I said, it's not as painful as you think. This is a very fast, easy way to do this. You have your, actually, let me change this around a little bit. We'll do, well, I had my amperage because I already had that. 0.004. So you have each one of these, 1 kilo ohm is equal to 0.001. gonna put this as G. Because G is equal to conductance, right? Yeah. No, 12 volts is voltage. What's your question? Oh, 12 divided by 1 kilo ohm. Yeah. Voltage by resistance gives you current. Yeah. Okay. So, let's look at it more theoretically. Okay? What would happen to my total resistance and my total current if I put a switch right there and I make it open? So in other words, these two resistors are open, they're not there. So what happens to my total current? My total current is now, instead of working with these two resistors as well, IT equals 24 milliamps. That is terrible. Milliamps. RT is going to equal 500 ohms. Okay? Why? I said this one's a really good one to practice, to look at this on. Why is it so? Why is it my totals change, but not my individual circuits? It changes the total, but it can't change the individual. Why? Goes back to what is not changing. What is always an application here? What's an Ohm's law? There's not changing. Okay? I still have 12 volts. That's not going to change. We're in parallel, right? My voltage is my voltage. It will not change. What about my current? Can it change? No. Why? Because I still have only 1 kilo ohm of resistance. My resistance has not changed. My voltage has not changed. Thus, my current cannot change. Does that make sense? It's kind of, like I said, this is why I wanted to have this example right here. Because this right here is the reason why I wanted to do this. Because you're changing the totals, you're not changing the individual. If that makes any sense to everybody. You're changing your totals, not the individual. Okay? Another way we could think about this is that if this is a 4-lane highway, and I shut 2 of them down, shut down 2 lanes, does that mean I can get up those other lanes any faster or slower than what I can? No. My overall movement goes up. So let's put it this way. Everybody's been out on 280. How many of y'all hate being on 280? How many would rather avoid 280 entirely? We can all raise our hands because 280 is probably the worst road in Birmingham. We all agree to that. Okay. They keep opening more lanes on 280. Why? They're trying to ease the traffic flow. They're trying to create more paths for people to go down. Well, we're not worried about traffic lights. Traffic lights would just be another form of a resistance, right? And everybody has the same traffic light. All right? So whenever they add more lanes, are more cars able to go down the road? The total cars can, but you can only have so many cars in each lane. You'll see what I'm saying? If I close one lane, I still have only so many cars that can go up a lane. Close another one, same thing. Only so many cars. What I change is what? The overall amount of cars I can put up that lane in a certain time. Does that make sense? The whole reason they keep opening more lanes on 280 is to try and cut the travel time. Not so much cutting traffic, because traffic is traffic. It's not going to change. Each lane can only hold so many cars and can only go so fast. But because you open more lanes, you allow more cars to move. The more lanes you close, the fewer cars will move. 280 is backed up. It'll always be backed up. It's what 280 is. 280 is 280. It is the one road everybody in Birmingham loathes anytime any of us are told we have to go over there. Why? Because the traffic backs up. We never know why. Because by the time you get to the end of the traffic, you're still sitting there going, why? Why was it such traffic? What is the congestion from? Imagine the gas in California is $5 a gallon at least. Yeah. Now Hawaii, I believe, is higher mainly because you're having to get it shipped from the rest of the world to the islands. And yeah, Hawaii is in the middle of nowhere. If you look at it in the ocean, it is middle of nowhere. We won't talk about the history of Hawaii at this point. It is a very interesting history lesson, and it is not one I want to get into tonight. All right, so everybody kind of got an idea of what parallel circuits are? Like I said, it's not the individual that will change, it's the total. Like I said, the biggest concept you have to remember is Ohm's law and Watt's law still apply. It is not going to change per branch. It will change the total. You can make sure you memorize that about this circuit. You're much better off for the next test. Tell you that right now. All right. All right, so just for giggles, let's look at circuit 3. I want y'all to go ahead and work to solve it for the next few minutes, and then we'll come back and reconvene and see how everybody does. Just kind of see where you're at. In the meantime, I've got 2 worksheets. I will say they are due for next class. Okay? Next Tuesday. Next time we have class. And of course, I draw it. You know what? I think a better idea of this would probably be take one and pass it. Take one from each stack and pass it. Might be a little easier and less me fumbling around there. All right. 2 sets. Take one, pass it down to your neighbor. That way. All right. So take one of each stack, pass it down, or pass the stacks down rather. Down. Yep. So there's 2 worksheets there. And we will go over them next Tuesday since we are not going to be here Thursday due to it being Veterans Day. Yes.
Oy, yo.
That is your homework for right now. Whenever y'all come back, I will give you the big packet for parallel.
We gotta do every single one of these.
Yes. That is your classwork homework for parallel circuits.
There's no such thing as like -1 or 2 for each.
No. One from each set. They really are not that, well. The most challenging one is the last one on this page, the one that's got, the one that's got the most circuits. The last one might give y'all a bit more challenge. I will go ahead and tell you now. Not as hard as what you think it is, but it is rather difficult. Okay? Let me draw it up here so I can explain it. I'll tell you now, guys. 100 milliamps, this guy right here, the very first one, that applies to all 3 of these resistors. Okay? That's going to divide into each of those 3 resistors. The 20 milliamps strictly applies to R4. Of course, your voltage goes to everybody, so it's 50 volts. If you have trouble with that one, it's fine. We'll go over it on next Tuesday. But just to kind of give you some clarity, 100 milliamps is going to divide into R2, R3, and R4. The 20 milliamps goes strictly to R4. So you should have your current for R4, R3, and then you find whatever's left of that 100 milliamps for R2. Does that make sense? Okay. So, how's everybody coming on circuit 3? Everybody done? So the first thing I need to do is divide my voltage everywhere so everybody gets 25 volts. $12.5 milliamps, 8.3 milliamps, 25 milliamps, 4 kilo ohms, 6.25 milliamps. Okay. Next thing I need to find is my conductance for each one. So what is my conductance for 1K? So 1,000 to the -1 or x to the -1 should give you 0.001 or 1 milli. What about 4K? Oh, hold on. 0.325. It's 250 micro or 0.00025. All right, so I'm writing this two different ways up here just because I'm kind of trying to give y'all an idea of what some of this is. When I put 001, that's 1 millisiemens. Siemens is the unit for conductance. So 3,000 conductance would be 0.0003 repeating, or 333 micro. You take it to you push in either x1 over x. The button is either 1 over x or x to the negative 1. So what is my 2 kilo? So 500 micro, 0.005. Okay.
We have to do local like flip it, or we can just do it straight out.
It depends on what you would prefer to use here. The whole reason I'm doing it as the decimal and as the milli and micro Siemens is just a different way to illustrate the conductance. It kind of depends on how you prefer to enter it into your calculator. Some calculators, all you have to do is say 500 times 10 raised to the negative 6 would give you 500 micro. Other calculators don't do that well, and if you try and do 10 to the x, it generally does not work as well unless you've played around with it enough to actually know what you're playing with. So some people prefer to see it written in decimal. Some people prefer to work with it written as its different way of writing it. So that's kind of why I'm trying to do it both ways. So in decimal format, it ends up being 3.083 repeating, or, I'm sorry, that's 0.0038, I'm sorry, 3.083 repeating, and 3.083 millisiemens. Either way, when you take it to the negative 1, RT is 324 repeating. It repeats it as 324. It says 324.3243247. I think it only did that because I eventually stopped using the 3 repeating. So the other way we would look at this is to find IT. Okay? What is my current total?
$71.75.
Hold on. Point 0.00125 plus 77.083. Did you make sure you put in the 6.25 for the 71? The person called out 71? Because what I get is 77.083. What about everybody else? That is milliamps, by the way. All right, so I take my current total that I have found and divide 25 volts by my current total. What is my resistance total? Is it anything like what we found using our conductance? What you got? G equals our inverse of G. V divided by I equals at least that's what I got. How about the rest of y'all? So the conductance works, and it is something you might want to practice. I'll go ahead and tell you now, when we get to series parallel, that's going to be the norm when trying to work with parallel and series circuits, guys. So it would very much benefit you to go ahead and get working with these down, because I'll have to show you that kind of circuit at another time. But when you get parallel and series circuits, you're going to have to be able to find conductance, and remember that that's how you find resistance total for those type circuits. Huh? The very bottom is the 2 different ways I displayed conductance. So I had the decimal format and I had the metric notation format. Just as a way of, for those people that prefer to work decimals, that's one way. If you prefer to work with the metrics, that's another way. I don't really have a preference since I've been working with this so long that I know the metric versus the decimal notations backwards and forwards at this point. So for me, it just really is a different ways of writing the same numbers. Yes, I'm recording this. Yes.
So all the sheet, everything on the worksheet.
Yes. And like I said, Tuesday we will be going over those worksheets. And we will go over every question on them, and we're going to work them as a class. If you want to work them as teams for the first 30 minutes of class, that's fine. You can work them as teams and kind of go over who's got what and see what you did and how they did it. There's a lot of different ways to do this. I'm trying to find ways to help y'all make this fun and kind of help it stick. Because parallel circuits are kind of the basics of how all of this actually works. I will say that the video, while it is picking up on me speaking, since I am not writing this with a mouse, it is not going to appear actually on the screen. So you'll hear me talking about it, and you can take pictures of this, but it won't have it on the board. Okay. Everybody good? Any questions? What kind of questions everybody have? Mm-hmm. X to the negative 1, or x divided by 1, or 1 divided by x, rather. So, yeah. Inverses are pretty much standard things that you find on most calculators. All it takes is press of a button. Huh? That's why I said when we come back on Tuesday, considering how much I know that people forget over a couple days versus a week, I think for the first hour of class on Tuesday, I'm going to set y'all each in your own pairs or groups that y'all want to play in and let y'all work these problems together and see what each of y'all kind of come up with before we do them all as a group. All right. Once you find this right here is your conductance total, these two numbers, the 0.003083 and the 3.083 millisiemens. That's your total. That's from adding all those. When I get this total, I press that little inverse key again. That's what gives me this. This one is my inverse of G is equal to RT 3.24.3.24. Mm-hmm. Yep. That's when you get your RT. Erase this. All right, everybody good for a minute? Anybody got a question? What's up? Yes, that's about 10 points that I take out. So while it's something that you might forget, I try to make sure that you don't.
Oh, so this, your resistance total, you
Look
would
up,
inverse it.
okay, so up here, right here, we have a 1 kilo, 4 kilo, 1 kilo, 3, and 2. Where should that actually have equaled 324 ohms?
Am I doing it wrong? Are you supposed to add it all, right?
Like the first time I
Right.
followed, I just added all
Okay,
of
so
them. Well, I got like 0, like
Plus
0, 0, 0, 5, and I added all of those as well. You get that,
1,000
I got 0, 0, 3,
plus
0,
1,000
8, 2.
plus 1,000.
Pretty much the way I did it, it's like 0, 0, 0, 0, 0, 0,
Second, Angie, engineering notation, a little bit faster.
90.90 and they get 6.
Does that give me my RP?
No.
Does that give me my conductance?
That gives you resistance.
No, it doesn't.
Oh, no, it doesn't.
That 3.083 millisiemens is your conductance.
What's not beneficial?
No, it's not. You're not adding your resistance. You're adding the conductances.
Oh, so you gotta get each conductances, then add it all together. And then that will get you 3.083. Okay. Yeah. But why total 324?
Because once you find your total conductance, then you inverse it to get your total resistance.
And now if you do 3.083 inverse,
What you're doing, okay, so put it this way. Every time you add another load in parallel, you reduce the overall resistance in the circuit. Okay? So I'll put it to you this way. They open another lane on 280, right? That reduces the overall cars that you have to move up that one lane on 280. Does that make sense? So let's say, let me draw this up here because I think this might make it work a little better. All right, so let's say I have a one-lane road or a one-lane run, okay? So one lane to get me all the way up that road. And I've got 10 cars, we'll just, I've got 10 cars that have to get up that road, okay? And it takes forever because they have one speed limit they have to go, they have lights they've got to go through and everything else, right? So in order to reduce the amount of resistance I have to get up this road, I open another lane. So what I do is I have the ability now to take some of these cars and now they're traveling this road. But it's still taking forever to get them all up that road, right? So I open another road. It's reducing the load that this road has to go on. So we'll take another 3 off here. It reduces the amount of wear on the roads overall. Does that make sense? It increases the speed on the roads overall. Does that make sense? No, you do not have to find the conductance. But it's something I recommend you get used to. Because series parallel, you don't know how to do the conductance of it. Because the series parallel, we kind of already have the series parallel.
So think about, you change it, like this. solve it all. And you convert it to resistance.
Now to solve for resistance total, you have to find that and then add it to these. Now you see the problem, right? So if you don't have no this right here, well, this three or something.
Yes, and we didn't go into the micro cities and,
No, because you're dealing with bigger pieces and you're gonna get.
and he was only worried about just round those.
And that's fine, but what you're dealing with is a lot smaller, but it can be just as powerful, if not quite harder, than HVAC controls. Don't say them all together, but they're going to be at a different power. Then let's say, electrical. If you're dealing with a panel that deals with 5 amp, 15 amp versus 20 amp. You're having to put all these loads and calculate and know what those loads are. Because if you have one load too many, you're gonna burn out. And these million micro amps also become very important. Because the more loads you add, you have to think about what a homeowner does. How many loads have you put into the circuit? Yeah? Think about it this way. All the loads in your room. You have the TV, you have the stereo system, you have your lights, you have all the plants in your room, you have radio, music box, whatever. You have your plug-in for your cell phone, your plug-in for your earpods. You have your tablet. You have your wife's tablet, your wife's earpods, your wife's. Now you start seeing. Yep.
Like, when we connected everything was in series, and then there was parallel, it was interesting.
I'm gonna go ahead and stop this while everybody's kind of digesting it. Yep.